Hi, my name is Colin Maria, and today I'm going to talk about the population model and how we can tell when population will go extinct. This comes from chapter 2 in our textbooks, which deals with first order differential equation. Let's dive in. I chose question number 39 for my presentation number 1 for chapter 2. From chapter 2. This is my question. Learning objective. By the end of this presentation, you will know three things. First, how to turn a real world population problem into a math equation. Second, how to solve that equation using something called an integrating factor. And third, how to use the solution to tell if the population will survive or go extinct. Problem statement. The equation we're working with is dp over dt equals kp minus h, which is provided right here. Here, pt means the population on time, k is how fast the population grows, and h is the constant number of individuals removed every time unit. The question is, for what starting population would the population eventually go extinct? And we're about to find that out. Model differentiation. Model differ Differentiation. This model comes from two ideas. First, population grows faster when they are larger, so the growth rate is proportional to P. Second, we are removing a constant number of individuals each time period. A real example would be fish in a lake, where the fisherman catches a fixed number of fishes each day. When we combine these ideas, we get the equation dp over dt equals kp minus h, which is right here. For solution steps, to solve the equation, we first write the standard form. Then we find something called an integrating factor, which in this case is e to the power of minus kt. We multiply through by that, which makes the left side easier to work with. Then we integrate both sides. To solve for PT and use the starting population of P0 to find the constant. Our final solution is PT equals H over K plus P0 minus H over K e to the power KT. Extinction conditions. To find when the extinction happens, we see when PT can reach to 0. For K is greater than 0, the exponential grows. So the only way PT can go to 0 is if P0 minus H to the over K is negative. That means that the starting population must be less than H over K. And since it can't be negative, the extinction condition is 0 is less than P0 is less than H over K, which is right here. So H over K is greater than P0 and 0 is less than P0. In graphical numerical illustrations, I provided the graph in the next slide so you can get a visual better look of it. This graph shows three cases of P0. This graph shows three cases. P0 is bigger than H over K, the population grows, and P0 equals to H over K. It stays the same. If P0 is less than H over K, it goes down to 0. The table also shows the number of specific examples. This matches our equation and confirms our results. And this is my graph. Interpretation and validation. In simple terms, if we start with less than H over K, the removal rate is too high for the population to keep up. So it will eventually die out. If we start exactly at H over K, the growth and removal balance out. If we start above H over K, the population wouldn't keep growing. Extensions and what ifs. What if we change the parameters? If H, the removal rate, doubles, the extinction 3 holds doubles. making extinction more likely. If K, the growth rate goes up, the three holes get smaller. The population has a better chance to survive. We can also make the model more realistic by adding limits like maximum carry capacity. Conclusion and takeaways. In conclusion, we learned how to make and solve a simple population model. We found that the extension three holds is when the starting population is between 0 and h over k. We also saw how changing the growth or removal rate changes whether the population will survive. The end. Thank you for watching.